So we have to be careful. This can be very confusing for starter of NWP. If you want the simulation to output the amount of ring for you, there are two variables available, the both one called ring NC, and one is called ring C. We talk about ring C first. So the name is accumulated convective precipitation. So convective. So this ring C is actually calculated by the convection parameterization scheme. Okay. And then ring NC, the N is non-convective. Okay, non-convective. So this rainfall is not calculated by this convection scheme. It is calculated by the microphysics scheme. So when you need to get the rainfall from the whole NWP simulation, you have to add them together. And then for in some of our web interface or in some of the code, we call it ring sum, but if you don't see it, you just add them together. Or when you analyze the ring produced by these two schemes respectively, you can inspect these two variables separately. So for microphysics, I will use the next slide. Cloud can be resolved. There are small cloud and big cloud, so some are resolved, some are not actually resolved. But inside the cloud, hydrometeors, that means these species, hydrometeors, can be in vapor state, in cloud water state, in raining water state, in ice state, in snow state, in gravel state, or some model may be even more complicated to have one more state. These are very small molecular length scale, so they cannot be simulated. We have to use some formulation to calculate the amount of them, to estimate of amount of them as mixing ratio. Mixing ratio is the weight of that moisture species over the weight of dry air. Okay. So the parameterization scheme that implements some form of formulation for them is the microphysics scheme. So basically, the aim of this scheme is to emulate the process by which moisture is removed from the air based on other thermodynamic and kinetic fields represented within the model. So you go back to here. The cells are quite small, so the model may resolve horizontal wind and variation of horizontal wind per cell. And then for vertical wind, also they have a resolution of vertical wind cell by cell. So if the cloud is large, and then within the cloud there is, well, within the convection there is updraft and downdraft of some length scale. And if your cell is small enough in the horizontal direction, such a vertical wind speed may be represented to have variation among the cells. So the microphysics scheme can take these varying kinetic fields in the model as input, and then do a better job of estimating the change of stage of moisture, in particular rainfall or snowfall, and then calculate such ring density. So this is what the microphysics scheme is about. And then for large cell, you will see that there will be only one W. W means that the vertical wind speed averaged over the cell. Also, so are other variables. So obviously, it cannot represent convections within the cell. However, in reality, convection do exist, no matter you use small cell or large cell. So the modeler needs to devise some formulation to estimate if there is convection within the cell that is not resolved, how much rain it will produce. So they have that different people have different formulation to use different method of estimating these raining processes or related processes, and then implement it in the corresponding scheme, turn it into a software integrated in WRF or MPAS, and then they will produce this ring C according to their formulation. Therefore, for large grid spacing, you need to turn on this convection parameterization scheme and add them together to be the total ring. But if you turn on the convection parameterization scheme for the fine resolution part, that will overestimate the ring. So if you add this one, or if you turn on this one, the total will be wrong. For small grid spacing, you will need to turn off the convection scheme. So that's what we have mentioned. For WRF, you can specify it. For nested domain, you turn off the cumulus parameterization scheme. For the coarse domain, you turn it on. But for MPAS and CPAS, this is the difficult part. You need to have some software implementation that handles such scale-aware aspects of the parameterization model. Basically, the implementation should gradually turn off, or well, something like you just multiply a factor. The factor will be near 1 if it is meso scale, and then the factor diminish to near 0, and if the grid spacing is small. There are many kinds of formulation to do such a scale-aware thing. So it depends on whether there is an implemented scheme already present in the software distribution. And actually, the science community is hurrying up in just this recent 3 or 2 or 1 years to add this scale-aware feature in the models. So you will see that even in MPAS, some are scale-aware. The GF scheme is of their version. This one is scale-aware, but these other may not be scale-aware. And then some more researcher maybe they do the implementation, and then they share the implementation to the open source world, and then for others to integrate. And then so scale-aware version of the parameterization scheme is coming, and you need to check the version and check exactly what you are using. So here are the introduction. Okay, some more complication. For raining and the distribution of moisture, we have talked about microphysics and then the cumulus scheme. But actually, there can be other schemes that are affected by them, or actually affect them the other way around. PBL scheme is one of them. You will you will see that QV, the mixing ratio of moisture, and actually some complicated implementation of PBL scheme will also alter QC or QR. You need to check in detail what each parameterization do. And if this scheme also change the moisture distribution of each column, and then it will affect these two. So the cloud affects radiation, and then radiation affects the downward short wave and long wave surface, and then the surface also emits long wave out at night or actually anytime. And then if there are cloud here, and then you will notice that at night, if there's cloud cover, then the variation of temperature on the surface is pretty different. So the parameterization schemes affect each other, and each model have a little bit different organizations of parameterization schemes. So you need to check the models. Okay. So the simulation usually involve simulating or having not really simulating, having a formulation that estimates these processes that include moisture saturation, how clouds are formed, and then droplet formation and growth and evaporation, how rain comes out, and then raindrop or snow or graupel or hail falling down. They basically they use some formulation to estimate them. And usually that involve representing the particle size distribution of the hydrometeor. So there are simple to complex model. Some model will involve physics only. Some model involve both physics and chemistry. And as you may know, there is a Wolf-Chem model adding a lot of chemistry also simulated when you run Wolf. So in that models, they are more complicated, and they have chemistries, models estimating concentration of aerosols, and then concentration of aerosols also affects cloud formation. So for simple model usually called single. You will see the name single moments. They are kind of simple model. And in single moments model, moisture distribution is described by only one thing. So one thing, single moment. Okay, that thing is the mixing ratio, which is a mass ratio of I have just introduced. So if you choose some simple model, and then in the CPAS cloud interface, you can specify what output variable to write to file. I think you may have experience on it. I'm not sure whether you use the search functionality. Moistures are involved in these output variables called scalars. Actually, it is not just one variable. It is an array of variables. So if you choose single moments model, at least you will see QV, QC, QR, QR, QS. And then for WS6 here, WSM6 here, 6 species. So also QG. And then this is actually source code from the something registry variable be present in model or QV, but for some variables like QC, they are not present if you turn off parameterization present or games. So SM6 is here. So if you the output variable will be available to be written to file for users. Catered though, they may use double moments to describe the distribution of the particle size of the rain or of the snow. So you will see two more things, N something, NI and NR. Usually, they only add meaningful things for, so this more complicated part is meaningful only for ice and rain. So you will not see this is called number concentration. You will not see number concentration for all the species, but only important species that if you describe it in more details like this. For the same mixing ratio, the droplets can be larger but fewer. But if there are aerosols, especially in the case aerosol concentration smaller, and it is related to process like nucleation. If there are more dirty particles in the air, and then there are more nucleation. But if the total amount of moisture is the same, then it is just distributed into more numbers, larger numbers of droplets, but each droplet may be smaller. So in terms of raining, there may be fewer rain because it can still be suspended in the air. But if the same amount of moisture but clean air, then the droplets may be large, and then the terminal velocity of droplets falling down can exceed the critical value, and then it will become rain. So if a more complicated model have this detail, then the estimation of rain may be more accurate. But just maybe you have to do a lot of experiments to check whether a more complicated model is really more accurate. That may be or may not be. So this is what microphysics is about. You may see in CPAS the choice for microphysics for convection permitting grid spacing. The default choice actually changed to be not just a single moment model. It changed to some model called Thomson, which has, as I have just shown, it has NI and NR. Now this is the screen capture after I changed to use the convection permitting suites. So it has this feature, but the computational cost is higher. And then even for Thomson model, there can be two variants of model. The model present in CPAS is one that is non-aerosol aware. So there can be some even more complicated model involved that are not present in CPAS and CPAS. And then now we can talk about convection parameterization. So these are slides taken from this author from Anka. And then you from Google search will see beautiful slides and plain slides, but you have to take out important findings from Google search. So if you cannot do Google searching well, what you can do is to go back to these papers. And then if you don't want to read paper, you do some Google searching and find the appropriate learning material by yourself. So this is one I found. Cumulus scheme, usually for grid column, as we have already said, very often when we do some drawing, we are lazy. We just do the drawing, 2D drawing, and then show the horizontal map showing hexagons only. Actually, there are a column stacking up the cell, and usually in MPAS, usually we use 55 vertical layers, and so most parameterization schemes are doing the calculation column per column. Okay. Usually, what they need to change is the vertical distribution of the quantity, like mixing ratio or horizontal momentum. They redistribute or do some mixing of the quantities within the column. Okay, they are one-dimensional parameterization scheme. The one dimension involved in this scheme is the vertical dimension. Okay. So column. The grid column completely contains the convective clouds. So it redistributes air in the column according to the vertical convective fluxes, like updrafts and downdrafts. And then usually the schemes need to take care of when to trigger such convective column and how fast to make the convection acts. And about triggering, I think you are experts, and since I actually not studied atmospheric science very much when I was in university, so they use convective available potential energy to estimate where the convection is triggered, and then they also use a convective inhibition CIN, and then it involves a minimum cloud depth from the partial ascent. So basically, they have take this as input or estimate it, and then take the estimated quantity as input. And then usually they will estimate the mass flux in these parameterization schemes. And then they estimate, usually the schemes are classified into whether it is mass flux scheme or ensemble scheme. So out of the choices, these KF, TKE, actually it is difficult to pronounce it, and some other schemes, mass flux scheme, they have some estimation of based on mass flux. And then they will estimate ring. And for GF scheme, they will use an ensemble of triggers to estimate the amount of ring. So these are quite difficult topics, but I just want to show when you choose it, if you go into the detail, you can read that paper and then understand the mechanism behind how they do the formulation. And then some schemes quite similar. They have similar name. This is just a new one. This new one is from ECMWF, and many people trust it. And then there are different names, but actually based on other methodology like the ensemble method in estimating the triggers. So you either use some method to determine what you choose to use, or you understand it, and then also do experiments to evaluate which one is more accurate in what situation.